Okay, so second week, second lecture. We will start talking about this concept that is called the direct geometric model of a robot, and about joints, links, degrees of freedom. We're going to see what all of these things are, and yeah, some concepts that we will talk about. How do we model a robot using what we learned last week? What is the work envelope? What kind of joint types we have? What are links? And eventually this direct geometric or direct kinematics model. Okay? Small recap. What we saw last week. We talked about these 4x4 matrices, which we call them transformation matrices, homogeneous transformation matrices. Okay? Here we see the three transformations, the three translations. And here we see the three rotations around each one of the axes. Right? You remember we use this to transform things in space, rotate and translate. And we saw that we do this by multiplying, for instance, a coordinate frame. Let me turn on the laser. So a coordinate frame and the transformation matrix. And we saw that the difference between multiplying from the left or multiplying from the right has a different meaning. So this is here how we represent the rotation from the left results in a rotation around the static frame, while a rotation from the right results in a rotation around a transformation around the moving frame. And we saw towards the end, a bit briefly, this concept of switching coordinates between coordinate frames. So if I have a point and I know its coordinates in one frame, let's say P expressed in coordinate frame 1, how can I calculate the coordinates of the same point in another coordinate frame, let's say P0? We do this by multiplying the transformation from the frame 0 to frame 1, multiply from the left with the coordinates of the point expressed on coordinate frame 1. Okay? We saw that this is useful when in robotics, when we have different systems knowing things in their own coordinate frame. Okay? You practiced a bit with this in the laboratories, and we will use it again today. We'll see more examples with this again today. Okay? So this is what we did last week. Now, robotic modeling. To describe a robot, we need to know its structure. And in this course, we're mainly going to talk, as I said last week as well, we're going to talk about this type of robot, these articulated robots, or sometimes you will hear them as being called robotic arms, because they look like an arm. Okay? Like a human arm. And what do you see here? What elements do we have? We have some structural elements that are connected together, and some elements that allow some rotation or some translation. Okay, just again to clarify the terminology, the structural part, we call them links. That's how we usually call them. Okay, which they are stiff and rigid, so they don't deform. They do deform slightly, but we don't include this kind of modeling in our consideration. That would make the modeling way more complicated, but we can consider them as non-deformable. Okay? They can have any kind of shape. According to the design of the robot, you will see different robots with very weird shapes. It doesn't matter. As long as they are rigid, they don't deform. Okay? And how are the links connected together? They're connected with joints. Okay? So links do not allow any deformation or any movement, but the joints allow movement. That's the difference. Okay? Is this clear? Yeah. So we mainly see two types of joints in robotics. Okay? The first type of joint is called the revolute, like this new credit card that you know of. Anyway, so you might hear it being called we usually call it the revolute joint. And it's a joint that allows to change the orientation of a segment by rotating around a fixed axis, around one axis. Okay, so we have one axis and it allows rotation around that axis. The axis can be oriented however we like, but it only allows rotation around that one axis. Okay, you can think of it as a hinge of the door. Okay, that it allows to rotate the door around the fixed axis of the hinge. And other examples. Okay? And the other type of joint that we'll see is the prismatic joint. Sometimes you might call it translational joint, but the terminology correct is prismatic. And a prismatic joint allows motion that changes the position of a segment or a link along an axis. So it does not change the orientation as the revolute joint. The revolute joint changes the orientation. The prismatic joint changes the position, okay, but not changing orientation, keeping the orientation the same. So it's basically like a sliding element, okay? And again, it allows translation or changing in position along one axis, okay? It doesn't translate in two axes, okay? Now, it says here they can add 1 degree of freedom to the robot, the same as the revolute joint. Here, they can add 1 degree of freedom to a robot. What is degree of freedom? What do you understand when we say degree of freedom?
This in one direction or rotating in one axis.
Mm-hmm. Okay. Something there with movement and rotation, yes?
Degrees of freedom basically means how many ways can this object move in.
Okay. Almost there. There is one important word missing. Okay, so how many ways can the object move, you said, right? Or
rotate.
Or rotate, yeah, movement, yeah, it doesn't matter, yeah. Any other?
It's actually the opposite. Like how many movements are restricted to that object. Doesn't have to do that as well.
Can be as well. But let's see one example, okay? Let's draw a very simple robot. This is the floor, okay? And there is one joint here, one revolute joint, so one rotation, and there is a segment here, a link, okay? Simple thing, a stick and a joint here, we can control the position. And yeah, how many degrees of freedom do you think this robot has? It can be a robot. Why 1? Because you said that it has to do with in how many ways can the robot move, right? So let's say I have 2 dimensions here, and the robot can move, you know, I can change both the x and the y coordinate of the robot, of the end of the robot.
Yeah, but you're talking about the joint respectively, not the arm of the robot.
Sorry, once again?
Are we talking about the joint itself or the robot?
We're talking about the robot. What can the robot do, basically? That's when we're talking about the degree of freedom of the robot. Yeah, so that's a good observation. Talking about the robot itself.
It's not technically 2 degrees of freedom because the translation movement is not separated from the rotation.
Correct. Okay. So that's a good word, separated. Okay. Or another way to say it.
How many distinct?
Or another way to say it, independent. Okay. In how many ways can my robot move? Let's say the end effector of the robot, so the final point of the robot. Okay. How many coordinates can I change independently? Okay. So this robot can move along this plane, let's say, so I can change the 2 coordinates of the end effector, but I cannot change them independently. I cannot change the x coordinate without changing the y at the same time, because this robot will be constrained to follow this circle, this arc. I cannot put it in another different x position, keeping the Y position the same. Okay? Or as you said earlier, I cannot change the position without changing the orientation, for instance. Okay? So that's another degree of freedom that would be there, being able to change the orientation as well. Just to show you a counterexample, let's say I have another joint here. Now, how many degrees of freedom does this robot have when we're talking about the end effector, the end point of the robot? Same thing, a stick here and another stick here. Why?
Because there is the same case as previously with the single robotic arm, but also now the joint moves with the endpoint of the first part of the arm. So it also translates on Y.
Okay.
And around X and Y as previously when it moves around the second joint.
Basically, because I can change two things out of, we'll see how many, independently. What are these two things? One example is the X and the Y coordinate of the tip of the robot, of the end effector. Okay, so I can change, for instance, the X. Let's say, I can change the X coordinate without changing the Y. So I can position the robot here. How? By one example, I'm not going to be too accurate with the lengths, but for instance, I can put it like this. Okay. By changing both both joints, the angle of both joints, I can change where the tip of the robot will be. I can change one coordinate without changing the other. So here I am at the same level on Y, right? Or I could have changed the Y coordinate without changing the X. I don't know how to draw this. Let's say I will have to put it somehow like this. Of course, the lengths should remain the same, right? I'm not drawing it perfectly. The idea is that I have the freedom to affect two coordinates independently. Okay? Nice. Let's see one more example. So I added 1 degree of freedom. How? By adding one more joint. Right? Yep. This thing is finishing fast. So I add one more joint and I added another degree of freedom. What happens if I add one more joint? So again, the same thing here. I have a revolute joint, a stick, a revolute joint, a stick, and another revolute joint and a stick. Now the end effector is here. So I had one joint, I had 1 degree of freedom. I added one more joint, I got 2 degrees of freedom. Now I have 3 joints. Do I have 3 degrees of freedom?
No.
Why not?
Because you can move around the z-axis.
Okay.
There are only 2 coordinates you can change
Yes.
independently.
But is there something else on the robot that might change besides coordinates?
Orientation.
Orientation. Okay. So besides the 2 coordinates, what can I affect on this stick? I can affect how it is oriented as well. Okay. So I can change X and Y independently with 2 ones, with 3 ones as well. So nothing changes. But I can also keep the same X and Y and have a different orientation. I don't know, let's say something like this. Okay, now the tip of the robot is at the same position, but it has changed orientation. Okay? So I have 3 degrees of freedom in this case. 2 degrees of freedom that are translational or position, and 1 orientation. Okay? Cool. What happens if I add 1 more joint? How many degrees of freedom does this one have? 4. With 1 we had 1, 2, 3, 4, no? No, you're thinking about it, so it's good. What is bothering you? Why it's not 4 the obvious answer? Why 4 is not the obvious answer? What would be the 4th thing that we could change on this plane? Hi. There is none.
Because we did not have discrete.
Sorry?
We did not have any coordinate.
So basically, it's these 3 things that I can change on this surface here. I can change the position in 2 directions independently, and I can change the orientation, but there's nothing else I can change.
We added a new way to reach a certain state.
Yes, we added more flexibility. Okay, so now the robot is even more capable of reaching any position and any orientation. Sorry for this. Okay, but we did not add an extra degree of freedom because there is none to add here. We don't have any more degrees of freedom. Okay, so I could add 20 joints here, but I will not add extra degrees of freedom, but I would add more flexibility to the robot. Okay, great. So just to see it as well on black and white, come on. Sorry. Yes, so degrees of freedom, when we're talking about degrees of freedom, we're talking about the coordinates that we can change independently, the coordinates of the end effector that we can change independently. You can think the orientation also as a coordinate, okay? It basically says that the example that we saw here, a planar robot with 2 revolute joints. So this case, okay, can vary independently x and y, but we cannot change the orientation at the same time. Okay, we could say that we can change one of the 2 coordinates, let's say x, and the orientation, but then y would not be up to us to choose. So I could say, okay, I want to keep the same x, okay, and the same orientation. I could do that. I don't know. How could I do that? Yeah, I don't know. It has to do with the drawings and so on. But yeah, I could keep the same x coordinate or the same y coordinate and the same orientation, but then the other coordinate that I didn't fix would be, you know, not up to me to choose. Okay? So it can be any combination of the 3 coordinates that I can change. Okay, so here you see also the example graphically with the 3 degrees of freedom. Yep. Okay? Now, these links and joints allow the robot to reach a certain space around it. Okay? It has to do with the length, it has to do with the type of joints, how they are oriented relative to each other, and so on. Yes. Basically, this area that the robot can reach, it's what we call the work envelope. It's like an envelope that the robot can work inside in. Okay, and based on different combinations of link and joints, we can have different work envelopes of different shape. We saw some examples also last week. You can have a Cartesian envelope, which is like a parallelepiped, a cylindrical or a spherical or different, more complicated envelopes. Okay? It doesn't have to be a symmetric shape. Again, it has to do with the limitations of the robot. It has to do with the limitation of the joints, because the joints might not be able to rotate 360 degrees, or might be limited. Like, for instance, also our arms, the elbow, I cannot move more than, I don't know, 170 degrees range of motion. Yeah? Same could be for a robot. So then the work envelope might be a weird shape. Okay? Now, even if a robot has, let's say, 3 degrees of freedom, let's say a robot like this, it might have less degrees of freedom in some part of the work envelope. It might lose some of its freedom, let's say, in some parts of the envelope. So here, for instance, you can see an example where we have this robot there. You can imagine that if I reach the extent of the work envelope by extending all the joints, for instance, in one direction, then the robot is losing some of its flexibility and some of its freedom. Okay? Just to give you an idea here, let's say this is fully extended like in the slide. At this configuration, can I change X and Y, for instance, independently? And keep the orientation how I like it? Yes? No? No, because if I try to move, let's say, in this direction, no, maybe let me draw it in a better configuration, even more weird, to make it more clear. Let's say it's like this. Okay, and these are the 3 joints. Now in this case, I cannot move on the Y direction without changing the X direction, because that would mean that the robot becomes longer somehow, right? Because if this is fully extended, it means it cannot go further in this direction, and if I try to move up, it's gonna curve back slightly, okay? So in this configuration, it's the same in this configuration, but yeah, it's a bit more complicated to explain. In this configuration, I have lost 1 degree of freedom, or 2 even, because also the orientation will change if I try to move up. So I don't have 3 degrees of freedom anymore. Okay? So the degrees of freedom in general have to do with the number of joints. Not always, as we saw, there is a limit. Like in 2 dimensions, we cannot have more than 3 degrees of freedom. But it also has to do with the current configuration of the robot. If the robot is in a weird configuration, then we lose degrees of freedom. We're going to see more about these kind of cases in the Jacobian lecture. I think it's in 4 weeks from now. Okay? Good. So we have defined these things for 2 dimensions. What about 3 dimensions? How much limited are we there with degrees of freedom? Do we still have only 3 degrees of freedom in 3 dimensions, or how many do you think we have? 6. Very specific. Which 6 ones? The translation around the 3 axes, obviously. Okay, but then again we have orientation in 3 directions. Okay, so I can change the orientation of the end effector. I don't know if this is my coordinate frame. It can rotate around here. It can rotate around here. It can rotate around the other axis. Okay, so in 3 dimensions we can have up to 6 degrees of freedom. Okay. Again, we'll see some examples. Here I'm saying that the revolute joints can add 1 degree of freedom. The key word here is can. Okay, they don't always add an extra degree of freedom. They can, and we'll see some examples. Any questions so far?
I have a question.
Yes.
The orientation of the end vector
Yes.
is the same from two positions if the same angle has the same angle, or if it points upwards, it is considered either way the same.
Basically, how do we define the orientation? I guess that's what you're trying to ask, right? How do we define the orientation so that then we can say we changed it or something like this? Very good. It's coming up now. So that's what we care usually in robotics. What happens with the end of the robot? Okay? Why? Because that's where we put tools on the robot. It can be a gripper, it can be a welding machine, it can be, I don't know, any tool that we want to control its position so that it does something. Okay, you can imagine if I want to use a robot to weld, you know what's welding? It's a technique for gluing together in a way metal pieces, and we have a tool with a thing. I need to control the position and the orientation of that tool so that it does the welding properly over time, okay? So I usually care about what happens at the tip of the robot. Of course, when we want to avoid obstacles and other more weird cases, I care about what's happening also between the tip and the base of the robot. But for now, we're going to stick to the tip of the robot. And we want a way to describe the position and orientation of the tip. Have we seen something that shows us position and orientation so far in this course? We only had one lecture, so it's not so difficult. Okay? So it prepares a bit for what we're going to see. So this technique of describing the position and orientation of the end effector of a robot relative to the base of the robot, we call it the direct geometric model or direct kinematics model, different ways. And it's a mathematical tool that allows us to calculate the position and orientation of a robotic point of interest, which is usually the end effector, as I said, but it can be anything. Now, I want you to get used to these two things together. I'm not going to say all the time position and orientation. We call this pose, the pose of the robot, which means the position and orientation of the robot, of the end effector. Okay? Pose. So basically, this direct geometric model, we use it to tell us what is the pose of the end effector if I know what are the angles of the joints and the lengths of the links and all the structural part of the robot. Okay? Basically, the lengths of the links, they don't change while we use the robot, but the joints, it's the thing that we're controlling. And by controlling the joints, we can control the position of the end effector. Okay? Now let's see a very simple example, and then we're gonna build on this. Let's say I have this robot. Okay, and I'll draw it here as well. Very simple robot. As you see, it has a gripper here, and I think to grab stuff. And I want to calculate the pose of the end effector of this robot, and I need the coordinate frame to express this pose on. We usually build a coordinate frame at the base of the robot. Okay? So I want to know what is the position and orientation of this thing here with respect to this frame. What are the coordinates of the position, and how is this oriented relative to this? Okay. So as I said, what have we seen so far that gives us information about position and orientation? What mathematical tool? The transformation matrix. Okay. So we encode this position and orientation using this 4x4 matrix in 3 dimensions. Here it's 2 dimensions, but you can think of it as 3 dimensions as well. And we use a 4x4 matrix to describe the pose of the robot. Okay? And these are the steps that we are following. So to define this direct geometric model, which is this 4x4 matrix, we first identify the links and the joints of the robot. So if you have like a drawing of a robot, you need to understand, okay, what is a link and what's a joint. So here we have a joint here, for instance, joint 1, joint 2, joint 3, and in between these are the links, the structural parts of the robot. Okay? We start, as I said, by attaching a fixed frame at the base of the robot. So everything that we describe will be referred to this frame, which is something that does not change. Of course, this can be on a mobile robot or an airplane or whatever, on a train, but we don't care about what happens beyond this frame. Okay, we just care about this is our fixed frame and the robot is moving on this fixed frame. Okay. So we attach this fixed coordinate frame at the base of the robot, and then we attach a coordinate frame at every joint. Okay, at every link at the position of the joints. Okay, so I have a coordinate frame here, for instance. Let's say this is Y, this is Z, this is X. Maybe I should use colors. So then the first joint is here, the first link is here, and I will attach a coordinate frame at the position of the joint. I can put the coordinate frame however I like, orient it. For now, I will just keep it at the same orientation as this one, let's say. Okay? Then the second link is this one. Sorry, I add another frame here. So this is X, Y, Z. And the last link is here, and I add a frame here. X, sorry, Y, Z. Okay? And then I calculate what is the transformation between each subsequent frame. Okay, let's call this, where are you? Let's call this 0, the green one is 1, the red one is 2, and the blue one is 3. So I calculate the transformation from frame 0 to 1, from 1 to 2, from 2 to 3, and 3 to... No, there is no 4. Okay? Then I stop. Okay? If you remember what we said last week as well, if I want to find out what is the transformation from 0 to 3, I can calculate what is from 0 to 1, from 1 to 2, from 1 to 2 to 3, and then multiply them together. You remember this part? I hope so. Good. So this is our drawing here. Now let's try to do this. What is the transformation from 0 to 1? What kind of transformation do I have? Is it a rotation? Is it a translation? Rotation, translation around which axis? What do you think? So to go from 0 to 1, I have what kind of transformation? Once again? Rotation around X. So I have my starting one is coordinate frame 0, the black one. I want to go to Z. If I rotate around X, then the X of the green one should be at the same position as the X of the black one. No, because it would be just rotating around that axis. Okay. And then the other two axes would be differently oriented. So the Y, the green one, would be different than the Y, the black one, because I had the rotation. Translation on z. So what would have happened if I had translation on z? The two z's would be aligned, okay, and the x green would be just translated from the x black, but the orientation would not change, and the green y would be just translated from the black y without changing its orientation. And that's what happens. The orientation does not change, so I just have a translation by moving on which direction? On the z direction. Okay? So my the first transformation, which is from going from 0 to 1, this is the notation I'm using, it's a translation on z by, let's say that this distance is 1. Okay, so it translated by 1. 1 meter, 1 kilometer, 1 centimeter, it doesn't matter. Okay? What is the transformation from coordinate frame 1 to coordinate frame 2? So from the green to the red one. You said the previous one, somebody else. So what is the transformation between the green and the red? Translation on z by this length here, by 2. So the transformation from 1 to 2 is again a translation on z by 2 units. Very good. What is the transformation from 2 to 3? So from the red to the blue. Who? What? Translation on y by 3. Y by 3. Very good. Okay. Good. Now, I want to find out, first of all, the position. Then we'll talk about the orientation. I want to find what is the position of this point here. Okay? Expressed in the base coordinate frame, in coordinate frame 0. So let's call this P, point P. And what am I looking for? I'm looking for P expressed in 0. Do I know somehow P expressed in another coordinate frame that is independent of how the joints are positioned? Do I know what are the coordinates of P always in this frame? Yes. Why? Sorry, once again?
For the coordinate frame, the last link is fixed.
Yes. Yes. Exactly. One small detail I forgot to mention is that these coordinate frames that we attached, they are attached on the link. Okay, so if this joint rotates, okay, the coordinate frame will also rotate. Okay, so let's see if this joint rotates. I'll draw just the last part here. So let's say if this joint is rotating and it's like this, then the coordinate frame will rotate together with the link. So then it will look x, y, z. Okay? Do you see it? So basically the position of this point does not change. The position of this point relative to this frame does not change. You can forget what happens before, and then the relative position is the same. Okay? Also, of course, it doesn't matter what happens to these joints, okay? Because this thing will rotate accordingly. So I know P in which coordinate frame in coordinate frame 3. So I know P3. What are the coordinates of point P in coordinate frame 3? Can consider it's on the same plane everywhere. 0, 0 minus P on 3 has coordinate 0, 0, minus 3. And I write it with this format that we saw, the 4 dimensions, the 4 elements. Okay? Sorry, minus 1. You're right. Got excited. Minus 1. Okay? So how can I find out what are the coordinates of this point in the fixed frame? You remember a trick that we learned how to go from P3 to P0? So what's the trick? What is P0 equal to? Once again, louder.
All of the rotation times P3.
But basically, that's one step further. Let's see what was the definition. So if I go from 0 to 1, from 1 to 0, it's R0, 1. If I go from 3 to 0, what should I write here? The transformation from 0 to 3, right? That's the same as there. Instead of 1, you have 3 here, right? Good. Now comes what you're saying. How do I calculate R03? By saying I go from 0, 1, 1 to 2, 2 to 3. No? The other way around? Are you sure? Why?
Because we're moving with respect to the absolute coordinates.
Okay, so let's have a look. So the first one would be R01. Clear? Do we all agree? So I go from here, here. Now, should I move according to this coordinate frame or this coordinate frame?
The first one,
Why?
because it doesn't move.
Okay, yes. I think I used a very simple drawing and that makes it more difficult. Let's say the robot was not like this, but it was, I have my fixed frame. Am I still in the camera? Yes? Okay. So I do it like this. Let's say the first joint moved, but the other joints did not move. Okay? So the first frame is the green one. So now how should I draw the green one? And now the green one will be aligned with a link, right? And the red one also will be aligned with its link. This is Y, this is Z, this is X. This is X, this is Y, this is Z. Okay? So this is the same robot, just that this joint rotated a bit. Now, I do the first transformation. Okay, I reach here. Now, should I move along the green axis to go to the next one, or should I move along the white axis? Huh? The green axis, right? So I should multiply around from the left or from the right? From the right. Okay, so 1 to 2. And then I should move along this axis, not this axis, to go to the second one, to the third one. So I should again multiply from the right. Okay? And this will give me R03. Okay? Let's quickly see what is the result of all this. Do you remember the form of these transformations? Right? You remember it? Should be like this. Right? Now, if I multiply them together, I can tell you that we will result. You can verify this. I shouldn't use the wet one. So the R03, I can tell you it will be one, and then this will be 0, and so I don't make a mistake. Yes, 3, 3. Because basically it's like I'm going here, there, just moving by 3 on the Z and 3 on the Y. Okay? And if I multiply this with this, I should get P0, so the position of P in this frame. Let's verify this. So what would be the result of this one? So this is a 4 by 4, this is a 4 by 1. The result will be a 4 by 1. So what would be the first element? It's this row with this column. Is it 0? This row with this column is 3. This row with this column, 2. We agree? So 1 minus 1 minus 1 plus 3, 2. And the last one will always be 1. You can see that this will always be 1 because here you always have 0, 0, 0. Here you have 1, and here you always have 1. So this will always be 1 again. Okay? So this is the coordinates of P on this frame. Okay. Does it make sense? So if this is 3, this distance is 3, this distance is 2, this distance is 1, and this distance is 1, it means that the Y coordinate is indeed 3, this distance, and the Z coordinate is this distance, which is 1 plus 2 minus 1, 2. Okay? And the X is 0 because it doesn't go out of the board. Okay? So this is how we calculate the position of the end effector. After the break, we'll see how we calculate the orientation as well. Unless you have questions, you can have a break. Questions? No questions? Okay, break.